Hello students, and welcome to our second video this week regarding conjugated pi systems. In the last video we talked about addition to conjugated pi bonds, particularly dienes like this one here. Now we're going to talk about another type of reaction called the pericyclic reaction. And we're going to talk about several different types of pericyclic reactions. So first I'll list the types, and then we're going to go into them one by one, starting with an in-depth look at cycloaddition reactions in this video. So pericyclic reactions are different from reactions that proceed via ionic mechanisms like most of the ones we've learned, or like by radical mechanisms like the ones that we learned in Chapter 10 of this textbook from Chem 212 and in our Chem 212 review when we reviewed it. So in cycloaddition reactions, there are no radicals, there are no ions. There's simply a movement of electrons in the formation of sigma bonds from pi bonds. And so the first one here, the first example is cycloaddition reaction. And so the mechanism arrows go like this. The two electrons from the pi bond here go into forming a sigma bond between this carbon here on the diene and this carbon on this alkene. Then the two pi electrons here go into a pi bond between these two carbons here. And remember, this is a conjugated pi system, so these electrons are really moving around right here in this diene. And finally, two electrons in this pi bond are shown to go into making a sigma bond here. And the result is that we lose two pi bonds, but we gain two sigma bonds. We ultimately have only one pi bond remaining, but here we have formed a ring. Another type is this so-called electrocyclic reaction, and you can see how this can result in the closing of a ring, as you see here. So again, these electrons are in a conjugated pi bond system with these three pi bonds here, or these three alternating double single, double single, double single bonds. In this reaction, we show the electrons from this pi bond going in to form a sigma bond between these two terminal carbon atoms here. And then these pi electrons are shown positioned here between these carbons. So a similar electron movement you can notice here. And again, here we lose one pi bond, but we gain a sigma bond. Finally, we can have a Sigmatropic rearrangement. And in this case, basically what's going on is that the position of the pi bonds is moving, and we're ending up with a sigma bond in other locations. So here, the electrons in this sigma bond go into a pi bond here between these two carbon atoms. The electrons in this sigma bond go into a pi bond between these two carbon atoms. And finally, the electrons from this pi bond go into making the sigma bond here. And so here, we have not lost or gained any pi bonds. The pi bonds are just in a different location on the molecule. So there are four characteristics of pericyclic reactions. First of all, you'll notice all of these arrows are drawn at once. There are not steps to the mechanism. The reaction mechanism is concerted. It's happening all at once. There are no intermediates. The mechanism involves a ring of electrons. These are moving around this loop or this region where there are unhybridized p orbitals and they can move freely. The transition state is cyclic, where you have partially forming sigma bonds, and we're partially losing these pi bonds. And finally, the polarity of the solvent will not matter, and this is because the transition state here does not really have any charge. There's no positive or negative charges like there would be in an ionic reaction. So changes in the number of pi and sigma bonds are what distinguish these from one another. As I said, in the cycloadditions, you're going to gain two sigma bonds and lose two pi bonds. In an electrocyclic reaction, you're going to gain a sigma bond, lose a pi bond. In a sigmatropic reaction, you'll have no change in the total number of sigma or pi bonds. They will simply change in their locations. So we're going to start by talking about cycloaddition reactions. This is also called the Diels-Alder reaction here, so-called 4+2 cycloaddition in this example here. And again, this is a cycloaddition in which we have an alkene and a diene, or a polyene of some kind. And we have the three concerted arrow mechanism. We lose two pi bonds, this one and this one, gaining two sigma bonds. the dotted lines, and the pi bond here is now relocated to these two carbons right here. And these are our two new sigma bonds, red. Notice that we have an X attached here. This is because these will not occur on their own necessarily. You have to give them a little help, and you give them a little help with this so-called electron-withdrawing group. And this notation here is the number of carbons that are being added. So there are 4 carbons on this diene here, and there are 2 on this alkene. And so we have a 4 + 2 cycloaddition. In terms of the energy diagram, so in all mechanisms, or most of the ones we've been studying, we analyze them in terms of an energy diagram with the transition state being the peak of the energy diagram. Here we have the reactants here and the product. So you can see that this is a exergonic reaction. It goes through a transition state in which the electrons, there's basically a 1.5 bond all the way around in the transition state. These sigma bonds are partially forming, these pi bonds are partially going away, and a pi bond is beginning to form right here, and that's the ultimate pi bond you see at the end there. So as you can see from that reaction energy diagram, most Diels-Alder reactions are going to be thermodynamically favorable, so the products will have a lower Gibbs free energy than the reactants, and so they're going to be favored at low temperatures, or they're going to be thermodynamically favored at low temperatures. There it's about the product stability, but at very high temperatures the retro Diels-Alder can predominate, and that's because entropy will be the dominant factor. So remember entropy, ways we don't have to calculate entropy in organic chemistry like we did in general chemistry. We just have to take a look at things like, are there new gases being formed? Those have greater entropy. Are we going to greater number of molecules or fewer? So in the Diels-Alder cycloaddition here, we go from 2 reactants up to 1 product, or down to 1 product rather. And so these are not going to be entropically favored reactions, right? Here, especially as the temperature increases. Remember the equation. This is one you should never forget. Delta G equals delta H minus T delta S. And so the entropy term here, going left to right, it gets bigger at higher temperatures. And so when the entropy term is very high, the reaction is going to go in the direction that is greater in entropy, which will be to the left. So these the lower temperatures emphasize the exothermic properties of this reaction, and thus make it more likely to go in the forward direction. The entropy increases, the reaction will be more likely to go backwards direction, which is called a retro. So here's that equation again, just a little bit better explanation. We can see that the negative delta H, the reason why this is so exothermic, and again, we should be able to analyze, not with numbers, but with general ideas, the sizes of these, delta H and delta S terms. In terms of delta H, this Diels-Alder reaction is very exothermic because pi bonds tend to be weaker than sigma bonds. The electrons are further away. When electrons are right between the atoms, they're very tightly held. That's a more stable arrangement. And so that's a stronger bond. So pi bonds by themselves, a double bond is 1 pi bond plus 1 sigma bond. The pi bonds are weaker. So we're breaking 2 weak bonds, right? And we're forming 2 stronger bonds because they're sigma bonds. And so this clearly results in an exothermic type of arrangement. Whenever we break weak bonds, but we make stronger bonds, we get more energy out of making those stronger bonds than we lost by breaking the weaker bond. And that energy goes out, making it exothermic. In terms of delta S, again, delta S is going to be negative because we have 2 molecules combining to form a single molecule. So in this reaction, the enthalpy term is negative, the entropy term is positive. So, the smaller the entropy term is, the more favorable the reaction will be because it will be dominated by the negative enthalpy term. But the higher the temperature there is, the more the entropy term will dominate, which is going to be a negative of a negative with the negative delta S, so altogether it will be positive. And when delta G is negative, that means the reaction is spontaneous. When it is positive, it means it's not spontaneous. And so the larger this entropy term gets, the less spontaneous the reaction is, and this term gets larger when temperature is increased. So ideally, the right temperature for a Diels-Alder reaction is between room temperature and 200 degrees Celsius. You don't want it happening very hot. Now, this, practically speaking, when you're doing these reactions, a hot reaction is nice because it proceeds more quickly. But it, so we would, a higher temperature would be good to a certain point, but past 200, it's going to be very bad because we'll have more reactants left at equilibrium than we get products. So a little bit of terminology related to these cycloaddition reactions is diene and dienophile. So the diene, di here meaning two, ene meaning double bonds, diene, so we have a diene here, and this alkene is the dienophile, meaning that it can react with the diene, meaning phile meaning love, or it's attracted to, right? So the dienophile should possess an electron withdrawing group. So a bare ethene like this, even at 200 degrees Celsius here, this high temperature, you're only going to get 20% of these molecules going on to form the product. So it's really not favoring product formation. But with the presence of an electron withdrawing group, this will significantly increase the basically the process of the reaction here. And the production of the product here. So with an electron withdrawing group, the reaction will be spontaneous. Without it, obviously it wasn't, right? When we say spontaneous, we should get at least 50% of the reactants turned to products here. At only 20%, we do not consider that spontaneous. So if, however, we attach a very electron withdrawing group with this very electronegative oxygen with this carbonyl, this will lead to 100% of the reactants being turned into the products, or very nearly 100%. So good electron withdrawing groups include ketones, or esters, or carboxylic acids, or the cyanide. And each of these will be good electron withdrawing groups. They could also be, there are others too, maybe a halogen, but anything that pulls electrons. And so these carbonyls are very good. Now, Diels-Alder reactions do have a stereospecificity to them. When the diene is reacting, it has to be in the position in this s-cis position, first of all, so that it can react in the cyclic addition. In addition, when this reaction occurs, if we have a electron withdrawing groups here, or whatever attached groups here, if these are in the cis position, we'll get a syn type of addition where the two groups end up on the same side of the ring that is produced. However, if we have the addition of if the dienophile here has trans positions on these two electron withdrawing groups, then the result will be an anti-type addition to the ring, in which they are on opposite sides. So here you see one wedge, one dash, and of course you'd have the enantiomer here too. You'll get both. And that's essentially because the alkene can come from, let's say this is, the diene here in the plane of the page. It can either come behind the page or from in front on top of the page. You'll get two different results there. Alkynes can also function as dienophiles, not just alkenes. When they do, of course, you don't end up with just a single bond here. So you can see when you use an alkene and you have these reaction arrows here like this, whoop, and whoop, whoop, that. You can see here that here you'll no longer have a pi bond. You'll have a sigma bond only, not the sigma and the pi. So here, if we have a alkyne, a similar thing will happen. It's like this, this. However, in this case, we're still going to have another pi bond there. So you can see we have a pi bond and still the sigma bond from before. So in terms of the conformations, recall from our previous lecture that dienes can exist in the s-cis or the s-trans conformation. But for the cycloaddition to occur, the diene must be in the s-cis position. So we can have that necessary movement of electrons, right? If we have this, it needs to go like that, and like that, and like that. But that can't happen if we have the s-trans. They're just too far away. And so we need the diene to be in the s-cis position. So dienes that are trapped in an s-trans conformation cannot undergo a Diels-Alder reaction. So this will occur if, for example, we have a diene that exists as a part of a ring. So this diene here is in the s-trans position. So we cannot do a cyclic addition with an alkene. However, if the diene is in the s-cis position, like we have here, cyclopentadiene, break down that name, it's like cyclopentane, but instead of cyclopentane, there's two double bonds. So we say cyclopenta, and we end it with diene, two double bonds. And if we have this kind of addition here, now these are in the s-cis position. So we can have a Diels-Alder addition here. We'd have, again, the normal arrows here. We do like this, and then like. So you can see, ultimately, this double bond, the one that's formed over here on the left, that one's right over here. And note that these are trans, these two groups, so they end up in opposite positions on the ring, up and down. In terms of the number of carbon atoms here, we have 1, 2, 3, 4 here. We have 1, 2 here. So this ring has 6 carbons around it. Then the bridge are these 3 carbons right here. 1, 2, 3. That's these carbons. 1, 2. This one carbon here. And of course, we can also have the enantiomer. That would be just this X. That would be if you just switch these. If this was switched, and these two right here were switched, that would be the enantiomer. So cyclopentadiene is very reactive in Diels-Alder reactions. In fact, it's so reactive that if you want to use cyclopentadiene for something, you've usually got to heat it up first so that you can increase the entropy term and cause it to break apart and undo the Diels-Alder reaction. So cyclopentadiene will react with itself in this fashion. So it's a little bit hard to see the mechanism at a certain point because you got so many lines everywhere. But we get the formation of this sigma bond here and this sigma bond here. So this is now a pi bond right here, and we still have this pi bond, which is located right. And for the entire structure here, we can see that these carbons. So if I call this carbon 1, 2, 3, 4. This is carbon 1, carbon 2, carbon 3, carbon 4, and then we have carbon, let's call this carbon 5 and carbon 6, just, for the purposes of keeping track of where everything is. This would be 5 and this would be 6, and then these are the remainders of the ring right here, the cyclopentane. This alkene right here is that one. And of course, this could attack from the top side or the bottom side, so you'd get to an enantiomer. Now, when bicyclic systems form too, there are new terms that we can use to describe the arrangements of where these groups are going. They are endo and exo. So when we use these, the exo term, and you notice that when we had these rings undergoing the Diels-Alder reaction, we always end up with bicyclic products. And so in terms of where these are positioned, we look where the bridge is formed. So the bridge is formed out of these guys right here. Bridge is formed right here. And so we can have so here we have a transposition. So each of these are going to be on the same side. But if we attack from one direction, we'll get them coming in from the bottom here. The other direction, they'll be over on the side. And so we can see here that the bridge has one carbon atom. This other bridge has two. So the endo position is syn, or on the same side as the side with the larger bridge. The exo position is one that is anti to the larger bridge, and so that would be opposite direction here, the larger bridge. You can see kind of the way it's drawn parallel here. It's going away from that. Endo is here on the same side, kind of on the down position here rather than the up position where this bridge is. So the electron withdrawing groups here attached to this dienophile, in this case aldehydes, they tend to occupy the endo positions predominantly. Often the endo product is the only one we're going to see. And this makes sense, right? Because there's kind of blockage here that's occurring when it's attacking. So it kind of makes sense. It going to stick out would be kind of approaching in the direction right here. It actually ends up being on the endo side more. So you'll get a predomination of the endo product rather than the exo product. So you can see how this works here. The endo transition state is also going to benefit from a favorable interaction between the pi bonds on the electron withdrawing groups here. So you can see this sticking out here in this direction. We have this interaction between these present pi bonds. Remember, there's double bonds here, so this is a like conjugated pi bond system all the way along the cyclopentadiene. If it comes here on the bottom with these groups facing this way, they'll end up on the same side as the larger portion of the ring, ultimately facing kind of this direction. The transition state here, that is exo, is higher in energy, and the reason is because the pi groups here are further apart and not interacting here. So you can see these pi bonds here have a positive interaction with these ones here, but now they're too far away, so you don't get that interaction. And so ultimately, this is a much lower energy transition state. A lot of times, this is a much higher energy transition state. And so you end up getting the endo product to a significantly more greater extent than the product. In terms of transition states, or in terms of the energy diagram, here's a depiction of that. So you can see this is identifying here a very great difference in activation energy. The activation energy to produce the endo product is much lower. The activation energy to produce the exo product is much larger. And an interesting side note here is that often the exo product can be thermodynamically favorable, but it's so kinetically unfavorable it would take forever to create. And if you look at the structure, you can kind of see why, right? The exo product here has these, what would look like essentially, like if we were talking about cyclohexane rings, it would be like the equatorial position, where the endo looks more like an axial position, right? So there's a bit more, crowding and steric hindrance that's involved here in the endo. So the endo is less thermodynamically favorable. However, the transition state here is so much lower in energy that you get a lot more production of the endo unless you get to very high temperatures. And in that case, the Diels-Alder reaction would not be favorable anyway. So only one regiochemical outcome will occur if the diene of the dienophile is symmetrical. So here's an example of that. We have a diene here that's symmetrical. It's the same on both sides. We can draw a line down the middle here and see it's the same on both sides. And so we end up with this product as we have seen. However, if we have an asymmetrical diene, so that's the case here, but the dienophile here is symmetrical. Same thing. We'll get this kind of symmetrical situation here in the molecule. So either way, we'll only have one regiochemical outcome. However, there are situations where both the diene and the dienophile could be asymmetrical, both of them together. So here's an example. The diene is asymmetrical. If you try to draw a line, down the middle here, it's not the same on one side as it is on the other, right? And that's also true on this diene. Is a hydrogen here that's different from the aldehyde. And so you've got two potential situations. You could essentially have this one where it reacts as it's shown here. And so if we follow these arrows here, it reacts just as shown. You're going to get this product here. Now, this is going to be the minor product, and you can perhaps understand why. You'll get this as the major product. That would be basically if we have the approach of if we have the same reaction, but instead we have the diene approach in this way. And so now the CHO here would be positioned anti, or in the opposite side, or para rather is the right word. We produce situated para to the methoxide here. And so one of the regioisomers is formed as a major product, and so this gives some regioselectivity to this result. The way to predict this is to consider the charge distribution of the reactants here. So we can see here that we have a lone pair here that is allylic, and so there is some resonance to this. So we can have this allylic lone pair, and so that's a 2-arrow resonance situation. This goes like this, and of course this is a more favorable way of writing the resonance relative to this one. It's a good exercise to think of why, right? Positive formal charges on oxygen are not so good. Negative formal charges on low electronegativity atom like carbon is not as favorable. However, just analyzing in this way helps us to consider positions where the electrons are moving around and could be in at any one given time. And so what we have here is we have 3 resonance structures. Here we have a pi bond between 2 atoms of differing electronegativity. So we can write an arrow there, putting the negative formal charge on the oxygen, but that leaves this carbon with 3 bonds and no lone pairs. So it has a positive formal charge. And now we have an allylic carbocation, and so there we could have the movement of those electrons, and now we have this positive formal charge here. So considering those locations of these positive and negative formal charges, you could have an attractive force that occurs, right? If this positive formal charge here is located in a position close to this negative formal charge, well, that will give us an attractive force that will help to pull these molecules together to react. And so that partial positive formal charge here exists on this carbon on the other side of the diene compared to the aldehyde here. And so that would be this carbon right here. It's kind of flipped upside down. And then we have that negative formal charge residing on this carbon, partially, right? Not completely, because electrons are traveling through here, through those resonance structures. So the result is that you can have, due to this resonance, you can have this attraction between this partial positive and partial negative, which will lower the energy of the transition state, and you will get the major product here being the opposite ends of this ring. So that's a bit complicated, right? But resonance, chapter 2, oh my gosh, resonance comes back to haunt us every time, right? It's extremely important to understand resonance and how that can affect the way that these reactions will occur. Now, a better, or maybe in some ways superior, description of cycloaddition reactions can be given by molecular orbital theory. Now, molecular orbital theory, in the past, I have to admit, it's been shown throughout the book. It's been somewhat useful. We've seen it, but it's mostly been useful in this chapter, right? Because comparing kind of a valence bondish theory to molecular orbital theory kind of really helps to analyze where these electrons are traveling and what are the molecular orbitals that have the most electron essentially liberation or movement, liberal movement here, and which have less. And when we do these cycloadditions, we're going to want to consider the molecular orbitals of both the dienophile and the diene, and see where these orbitals can overlap most favorably. And for that, we're going to have to look at the HOMOs, the highest occupied molecular orbitals of each of these two, and the LUMOs, the lowest unoccupied molecular orbitals of each two. Now recall that we analyzed these molecular orbitals for butadiene, there being 4 pi bonds right? Four unhybridized p orbitals in butadiene. So one on each carbon. These are all sp2 hybridized. So they all have an unhybridized p orbital. And so we have the four of them shown here in this molecular orbital context. And we can see that if they're all aligned, the electrons can then travel freely between them, this being the lowest, a kind of valence bond type depiction of the lowest energy molecular orbital. The next lowest energy molecular orbital will have two sideways interactions between the p orbitals, but one node in between. And this one kind of corresponds to this, like the way the Lewis structure is. There's no pi bond in between, although realistically, the electrons can move pretty freely all the way throughout this 4-carbon system. The next lowest energy, where it starts to become unfavorable, we have one overlap of p orbitals and two p orbitals that are not overlapping at all. And then on the lowest energy orbital, we have nodes between each and every carbon atom because the p orbitals are directly unaligned and opposite to one another. Likewise, with a very simple alkene, we have two molecular orbitals with the two, sp2 hybridized carbons. We have the lower energy molecular orbital where the two p orbitals in these two carbons are aligned here and sideways overlapping. And then we have the so-called anti-bonding orbital where they are unaligned and there's a node between carbon atoms and you don't get any pi bonding. And so here we have 4 p orbitals, each with one electron. The 4 electrons go into the lowest energy orbitals here, making the third orbital here the lowest unoccupied molecular orbital. Here we have 2 carbons, 2 unhybridized p orbitals, each with one electron in them, so the 2 electrons can then be in the lower energy molecular orbital here. Now, for Diels-Alder reactions, the highest occupied molecular orbital of the compound has to interact with the lowest unoccupied molecular orbital of the other compound. And the lobes of these orbitals must interact in the correct direction for this to occur. And so when we look here, the highest occupied molecular orbital here, well, you can see them right here. So let's see how they interact. For butadiene here, with the electron-withdrawing group, the dienophile's LUMO will accept electrons from the diene's HOMO here, okay? And so this electron in the highest occupied molecular orbital of the diene will then go and be able to jump in during the course of the reaction to the lowest unoccupied molecular orbital of the ethylene. And again, ethylene, we're talking about this guy here. Butadiene, we're talking about this guy here. Now let's look at the way these orbitals might overlap. So if we look a lot at the lowest unoccupied molecular orbital of ethylene, we can see that their lobes are unaligned. They're opposing to one another. However, if you look at the diene here, on the left side, so where these orbitals are, there's going to be on this carbon here, so this represents this carbon right here. There's a red one here. And so it's this lobe of the orbital showing on this carbon. And then there's a blue orbital here on the bottom. And so you can see here in the LUMO, also there's a red orbital on the bottom and a blue orbital on the bottom. And likewise here, blue orbital on the top, red orbital on the top. So these align. And so these p orbitals can now interact. In these are, well, they're not p orbitals, they're molecular orbitals, but these lobes of the orbitals can interact, and we'll have an overlap of the correct orientation of the orbitals, and they will make a bond. Note that when this bond occurs, the carbons change in their hybridization from being sp2 to now they're making only a sigma bond, no pi bonds, and both carbons now will become sp3, meaning this carbon here, they were, let's see, these two here and these two here, they were all sp2, but after the bonds were made, now they're all sp3 hybridized. So the way this is stated in technical terms is that The phases of the reacting molecular orbitals are symmetrical, represented by the same colors here. In other words, if there's conservation of the orbital symmetry, then the reaction will be said to be symmetry-allowed, as long as the correct orbitals with the same orientation here will overlap with one another during the course of the reaction. Similar to these Diels-Alder 4+2 cycloadditions, the reaction below is a 2+2 cycloaddition, so these can occur as well. Let's take a look at the molecular orbitals and see if this reaction is symmetry allowed or not. So if we look, if we look, we have two ethylenes, right? So the LUMO of one reactant must have the same symmetry as the HOMO of the other. So in the case of the butadiene, that was true, right? And the electron could jump over. We saw that in the last example. However, in the case of two ethenes, it's impossible for these to line up because remember what we had for ethene. Just going back here, or we can go forward here. This butadiene will in fact not be formed, and here's the reason why. If we look at one ethylene, one of them is where the two orbitals are aligned. That's the highest occupied molecular orbital. The higher energy orbital, the LUMO, is the one where the lobes are opposed. And so, in order for this reaction to occur, we would, on a normal ethylene, we'd have to have these two lobes be able to align with the lobes of the LUMO of the ethylene. So imagine these represent both ethylenes. We'd have to have the HOMO of one ethylene be able to overlap with the LUMO of the other ethylene, and that will not occur because the lobes are not aligned here. However, we can make this reaction occur if we expose the ethylene to UV light, because at that point an electron can be absorbed, and if it's the right frequency or right wavelength of radiation, this electron can be promoted to the second orbital here, higher in energy, and in that case, this will become the highest occupied molecular orbital. And now we can see for this excited ethylene, the highest occupied, the HOMO, can interact with the LUMO. We can have an overlap of these orbitals because they're both opposed on both of them. And so we can induce the reaction to occur. So the result is that 2,2 cycloadditions are only possible when light is used to excite an electron in one of the molecules. And in that case, the HOMO of one ethylene will have lobes of these orbitals that are opposite to one another, and so will the LUMO, the lowest unoccupied molecular orbital of the other ethylene that's not excited. And since they line up, the 2,2 cycloaddition can occur. And so under normal conditions with no UV light, this won't occur. But if we can expose these ethylenes to UV light, they can make a cyclobutane. So that concludes our discussion of these cycloaddition reactions. In the final lecture for this week, we're going to talk about the other two pericyclic reactions that we will be discussing in this chapter. The electrocyclic reactions, and the sigmatropic rearrangements. I look forward to telling you guys about those next time.